Okay, we're back to shear stress. We're going to look at shear stresses. That stresses in things like pins, bolts, rivets, and so on. This is just a couple of examples just to show you where shear stresses occur. If you look at this bolt, it's called a D shackle actually. This thing's a D shackle that I'm trying to highlight here. And this pin, this shackle here is got a pin across. Perhaps I should let me just get a line off it. This shackle here has a pin going through it. You can just about see the pin through here. That pin sort of goes through the shackle. It's a D shackle used for lifting items. A D shackle. It's a very, very strong piece of steel that's forged. But the pin I'm interested in, that pin is actually in shear, and it's actually what's called double shear. If you can see on the diagram, you have to break the pin there and break the pin there to actually fell the pin. So it's what's called in double shear, that pin that we're looking at, and we'll look at double shear in a moment. But that D-shackle pin again is a shear problem. If you've ever seen eye bolts that are used for lifting things, eye bolts, you have the rivet, the threads here shown diagrammatically, and these threads they're actually in shear here as well. All right, so you get shear in threads, for example. They have to be designed to take the shear stress. Again, another eye bolt showing the thread that's in shear. And apparently I'm told that the eye bolts, when they fail, they actually fail in tension across here, because they design the thread so that they will never fail in shear. It's always a tension failure, with a sort of a load applied here and reacted sort of here. They always fail in tension. They don't ever fail in shear. They're designed that way, I'm told. And that's another example of another collar eye bolt. Okay, so that's where we use shear stresses. We have to look at things like pins and bolts and all that kind of stuff. And that's what we're going to look at now, okay? Okay, so we're going to look at shear stresses. This should be in your notes. I'm looking at page 157 of your particular notes, but this is what's shown on the screen here. Now these calculations are very similar to what you've already done with direct stresses, because if you remember, with direct stresses we had a formula. I'm using symbols here, but we had a formula of the stress, sideways 6, was given as the force in the member divided by the cross-sectional area. And we were talking in those cases of having sort of pieces of bar, for example, like this, and we have a load applied, P, we called the P there, and we had a cross-sectional area sort of through there, circular section maybe, whatever, and the stress in the bar was the force applied divided by the cross-sectional area. So this calculation is actually very similar. This formula is very similar. The only thing that's different here is the symbol. Shear stress symbol is slightly different. It's actually it looks like a T really. It's like an italic T. It's called tau actually, Greek symbol. But it's still force over area. The thing that's different here, it's the shear force P over the shear area. And I sometimes put a little S against the A. You don't need to really, but I put a little S against the A to show it's a different type of area. It's a shear area, because in some questions you get tension areas and you get shear areas. So I sometimes use a bit less there, but you don't need to. But you can see the formula is very similar to this. Direct stress is force over area, and shear stress is force over the area in shear. But as I mentioned in the previous slide, we need to be careful with shear, because you can have a single shear joint, or you can have a double shear joint, and we need to be aware of that in the calculations. So if you look at the left-hand diagram here, this is a single shear joint. We've got a rivet shown going through two pieces of material, and to break this joint, to fail the joint, we would have to break the rivet in this particular place here. All right, we fail it just in that one location. Then we could bring the plate, we could remove the two plates. With the double shear joint on the right hand side, if we want to break this joint, we've got to fail the pin in two places. I've got to fail it here, and I've got to fail it here because of the design of the joint. The joint's in double shear, so the pin fails in two places. So it's a double shear joint. Okay. So when we're doing calculations with shear, we have to first of all think, is it single or is it double shear? Because that makes a difference to the area we use. If it's double shear, it's double the area. Okay, so that's something to be aware of when we're looking at rivets and bolts and so on. The example at the, below, example 1s, is exactly the kind of thing we're going to do in a moment. So this is a question to find the shear stress in a 6mm diameter rivet, shown in the diagram, when we apply a shear force, which is the P, of 2,000 newtons, 2 kilonewtons. I've worked this through in meters here, so I put my diameter, 6mm, into meters, so 0.006 meters. And the force of 2 kilonewtons I've written is 2,000 newtons. Obviously I can work out the area of the rivet, because that's what's in shear, is this area through here, that's in shear. And I can work out the area of that. I use pi d squared upon 4 to find my area, because I'm always given diameters in the question. But you could find your area simply using pi r squared. If you're more familiar with that formula, then use pi r squared to find your area. Don't forget the r would be half of the diameter, of course. So I can work out my area, pi r squared, and then I can find the shear stress. It's simply going to be the force applied, the P divided by the area. So 2,000 is the force, and the area is calculated above here in meters squared, divided by the area, gives me the stress, which is 71, it's meganewtons per meter squared is the actual answer. I think your books might say 71 newtons per meter squared, but it's actually 71 meganewtons per meter squared. Just add the m into your books. M stands for 10 to the 6, of course. Excuse me. Okay, so that's the basic calculation we're going to do. That's what we're going to do. Work out the shear stress in a joint, given the force and given the appropriate areas. All right. We'll obviously transpose the equation. Sometimes we'll be given the allowable stress or the working stress, and we'll have to find the force or the area. But we'll look at those later on. And one thing to note about shear stresses is that the area you're interested in, the shear area, is parallel to the force. So go back to this diagram here, you can see the force is in this direction, my P is in this direction, and the area is parallel to that direction of the force, that line of action of the force. When we were looking at the direct stresses over here on the right hand side, the force P was normal to, right angles to, the direction of the area. So that's why it's called a normal force or an axial force, direct force there, and this is called a shearing force, because the lines of action of the areas are, if you like, in different directions. I don't think it makes any sense to you, but that's the slight difference between the two stresses. But anyway, let's have a look at some calculations here. So this is now the questions you've got on page 157. I'm going to look at the questions together with you. So in this particular question, we're given 2 steel plates, and they're riveted together using 10 rivets. So you can see in the diagram we've got the 10 rivets. Each of the rivets is a diameter of 4 millimeters. We've got to calculate what's called the working shear stress in the rivets, in one rivet, if the applied load P is 2.51 kilonewtons. Okay, so let's take the information from the question. Let's draw a little diagram. I like to have my own diagram, so I'm going to draw my own little diagram here. So I've got 2 plates, my upper plate, okay, and I've got my bottom plate. So I just like to draw these for my own benefit. I know it's in the sketch, but I like to have my own little sketch I can quite easily doodle on. So this is my bottom plate, my lower plate. Kind of thing, right? And I've got 10 rivets, it says. So 10 of these things. So 1, 2, 3, 4, 5 in that row. 1, 2, 3, 4, 5 in that row. Okay. The force applied to the plate is, I'm going to put it in newtons, 2,510 newtons. That's the 2.51 kilonewtons, and then this plate will have the same force applied here. P is 2,510 newtons. Okay. Diameter of a rivet, one rivet has a diameter here. diameter D is equal to, I'll use millimeters here, 4 millimeters. Okay. So the load pass here basically is we apply a force of 2,500, say at this point here. That's in the plate, it's actually tension in the plate, and that goes into shear in the rivets. So 10 rivets take that in shear, and they put it back into tension in the lower plate. That's the sort of load pass through here. So we could check the plates for tension if we wanted to, and then we could check the rivets in shear. But it hadn't asked us to look at the plates, only the rivets. So that's what I'm going to do here. Okay. So the first thing is this a single or double shear joint? That's the first thing. Are those rivets in single or double shear? Well, judging by the diagram on the previous page, or on the top of the page you're looking at, they're actually in single shear, because each rivet, when you sort of look at them sideways on, is only in single shear. So if I just do a sort of sideways diagram, I've got my rivet going through, take one rivet for example going through the plates here, we can see to fail that rivet, if I put a load there and a load here, to fail the rivet I've only got to fail it in one place here, that location there, and the rivet would break. So it's a single shear joint. We've got 10 rivets here that are in single shear. So let's make a note of that for reference. So note a single shear joint. So in this case, that's 10 rivets in single shear. Alright, in this particular case, 10 rivets and each one's in single shear. So just note that for your reference. So we know that the formula we're going to use to find the shear stress, I'll just write it here. I'm going to use a little symbol, they do use this in the formula sheet, this little tall symbol, is equal to the force applied, we've got that in the question, divided by the area that's in shear. So I'm going to calculate the area in shear now. I'm going to find that first of all. So step 1, find shear area. Okay, so the area in shear is equal to, so looking at the rivets, I normally use pi d squared upon 4 for my formula for area. You use pi r squared if you're more comfortable with that. But the area of one rivet would be pi multiplied by the diameter, which is 4, so 4d squared upon 4 in this case. So I use that formula. You can use pi r squared, but don't forget you have to use 2 for the radius. So using my formula, pi d squared upon 4, that would give me the area of one rivet. But in this case, there are 10 rivets, so the shear area is the area of one rivet is multiplied by 10. So we do that on the calculator. So I'm going to use my formula. If you want to use pi r squared, feel free to do that. So on my calculator, typing that in, I've got the pi button up. So do we get 125.7 millimeters squared? On our calculators, just check that for me, make sure you're okay with the calculation. So there's my shear area, so that's for 10 rivets, alright? We've got 10 rivets there that are in shear, so the area of one rivet there, and I've multiplied that by 10 in this case. Now I can find my stress in the rivet, so I'll do that over here. So part 2, find shear stress. This will be in rivet, and I'm just going to use the formula above. So shear stress, I use my funny looking symbol, that's like a T, is equal to the P upon the area in shear. In this case the P is given in the question, 2,510, newtons and divided by the area above, so 125.7. Put that on my calculator. So 2510 divided by my 125.7 gives me approximately 20. It's 19.97 it says here, but that's approximately 20, and I'm using newtons per millimeter squared. My force was in newtons and my area was in millimeters squared. The newtons per millimeter squared are my units. In the question, notice it says 20 meganewtons per meter squared. They're just using the different unit there, newtons per meter squared. All right, so 20 newtons per millimeter squared is the same stress level as 20 meganewtons per meter squared. It's the same thing. So we've got the right answer. Okay, just different units. Let's go to the next question. That's question 1 then. We've got this D-shackle, like I showed you in the picture before. D-shackle here. High alloy heat-treated steel pin of the D-shackle has a 30mm diameter. We've got to determine the maximum load here. That will be the P. So when they say maximum load, that's the P value that the pin can support if the pin stress is limited to 60 newtons per millimeter squared. So 60 newtons per millimeter squared we're looking at. Okay, so basically what we've got here is a pin. If I just draw the pin from the D-shackle, we've got this pin across here. Okay, which is this thing here, this pin that goes through here. Okay, and it's basically got it would have a load applied to it, so there would be some kind of load. If you were lifting something, you know, there'd be a load here. Whatever that load's going to be, we've got to find it. P. Don't know what that load is, and it's kind of reacted in the D-shackle itself. It's sort of going back to our beam work. It's kind of got a reaction here and here, so it's got a double shear failure. We've got to fail it through here and fail it through here before we can break the pin. Okay, so it's a double shear joint in this particular case. So the first thing to write down is the pin is in double shear. So note, the pin is in double shear. Okay, get that from the diagram. We're given in the question the diameter of the pin. It's 30mm, so we know what the diameter is across here. So diameter is 30mm, so in a minute we can find the area of the pin. And we're also given in the question the pin shear stress. In other words, we're given the working stress for the pin. They're saying they're allowing the pin to work up to 60 newtons per millimeter squared. So in this particular case, the working shear stress, we use the term working because that's what it's allowed to see every day of its life, if you like, and that's a symbol, that Greek symbol tau. So that's 60 newtons per millimeter squared. So I'm using millimeters in my calculations because that stress is in millimeters here, so I want to keep all my dimensions in millimeters, so that's why I'm using millimeters here. So let's think this through. What we need to find here. It wants us to find the maximum load we can take. Well, that's P. P is the maximum load. So first thing we need to do is to find the shear area, and then using our formula for shear stress we can find the maximum load. So if I put my formula down here, shear stress is equal to P divided by AS. In this particular question we're given the shear stress. It's in the question. We can calculate the shear area, going to do that in just a moment, so we can find the P. So that's what we'll be looking for in a moment. We're going to transpose the equation. So let's work out the shear area first. We need that. Find the shear area. So the area in shear, now this is a circular section, so again I'm going to use my pi d squared upon 4 formula. So if pi multiplied by, in this case it's 30 squared upon 4. If you want to use pi r squared, then pi times 15 squared, that's fine, but I'm using my usual formula. And that's the area of the pin, but don't forget this is in double shear. So I'm now going to multiply that by 2 this time, not because there are 2 pins, but because the pin is in double shear. So you might want to make a little note for yourself here, as in double shear. Okay, so a little note there when you come back to look at your notes, you'll see it's in double shear. Okay, now we've got to work that out, whatever that works out to give us, that will be our shear area. So do the calculation now. So in my calculation I've got pi multiplied by the 30, which is squared, and I'm dividing it by 4, and I'm going to multiply that by 2. Okay, so that gives me a value of 1,413.7, and that's millimeters squared for the units I'm using. Okay, I hope you're okay with that. So that's the shear area that's been found. Okay, now we've got to find the actual shear force that we can take here. So part 2, find shear, they call it maximum load there, so find the maximum shear force, I'll call it. Don't forget load and force are interchangeable terms, so maximum shear force, maximum shear load. So I'm going to find that. Now if I rearrange this above equation, perhaps I should do it up here, the P would be equal to the shear stress multiplied by the shear area. That's the formula we're using. So I'm going to use that here. So P, and put it down here, P is equal to the shear stress times the shear area. In this case the shear stress that we're allowed to use is 60 newtons per millimeter squared, and we've just worked out the area above. So just going to multiply those terms together and see what we get for our value. So according to my calculations, that's 84,822 newtons we've used here, and they've got it in terms of kilonewtons. That's fine. Then we can also write that as 84.8 kilonewtons, approximate value. Either correct, value is correct, it's fine. Okay, so that's the shear stress in that pin, and that pin is in double shear. So again, I hope that's okay. Question 3S. We've got here a bolt. It's 25mm diameter bolt made from steel, and they've given us the ultimate shear strength of the bolt. We'll have to look at that in a moment. They've also supplied us with the factor of safety they want in the bolt design, which is 4, which we've got to apply to the ultimate strengths. We've got to find the maximum shear force. So it's a bit like the previous question. We've got to find the force, the P, that the bolt can take. So quite a bit of information here. Let's just take the information from the question and see where we go here. So we've got our bolt. It's 25mm diameter, so perhaps I'll just sketch that. And it's shown in the sketch here. Now looking at the sketch, can you see that the bolt's going to be in double shear? Because I've got to fell the bolt through here and through here to break the joint. So the bolt in this case is in double shear. So I've got my applied sort of force here, and it's reacted over here, and it's reacted here. Okay, so that puts the bolt in this particular case in double shear. So the first thing to note is the bolts in double shear. So I'll just do my own little diagram here. So I have my bolt here, little diagram of the bolt, a nut down here kind of thing. I've got my plate, so I've got a plate here, a plate here, and a plate here, and another plate here kind of thing. Not a very good drawing, but anyway, hopefully you get the gist of what's going on. Okay, there. Okay, and we've got our forces applied, so there's a force here, P. We don't know what the P is, we're trying to find the P, that's what the question wants us to find. It's kind of reacted over here, So yeah, so double shear joint, we've got to fail the bolt through there and through there. So let's put a note for that. The bolt is in double shear. Okay. Now this factor of safety thing, let's look at that. Now they've given us the ultimate shear strength of the bolt. Now if we go back to the stress strain diagrams that you've seen before, if you were to look at the stress strain diagram for a tensile specimen, stress and strain, go back to what we did a few weeks ago, you would find that the diagrams typically sort of look something like that, where this would be the ultimate tensile strength, we would call it, where the bolt actually failed in bits. If you look at a shear stress strain diagram, if I use the symbol shear stress, and there's a shear strain symbol, shear strain diagram, it actually looked quite similar in its shape, but it would have a lower value. All right. It would fail at the ultimate shear stress value, not the ultimate tensile stress value. And what they've given in the question is this USS value. They've given the sort of the stress level at which the pin fails or the bolt fails in shear, and that value they've given us in the question is 200 newtons per millimeter squared. Okay. So that's when it actually fails. It would fail in shear. A shear test is a totally different test to a tensile test. But the tensile strength is always higher than the shear strength. All right, and that's what we have to check out in shear. So this factor of safety thing, what that's trying to say is that we don't want to work the bolt anywhere near 200. That's sort of dangerous. If we work up to 200, you know, and we're slightly wrong with our values, or we've got a slightly corroded bolt or something, it's likely to fail. So that's not a good thing. So what they want us to do is to work, apply a factor of safety of 4. Now, if you remember from previous work, the factor of safety formula, this is back in your notes, we sometimes call it FOS, the FOS, is actually the ultimate shear stress or the maximum shear stress. So in this case, if I use the symbols, it's the maximum shear stress, using that symbol for tool, over the working shear stress. That's the actual formula I think we used in our previous notes. Okay. Now we're looking for the working shear stress. In other words, we've got this because this value is given in the question. That's the 200, and we've got this value is given in the question. That's 4. So if I was to transpose the equation for the working shear stress, that's the stress we can apply, working shear. For the working shear stress, we would just transpose that equation to this. Just a bit of transposition, 3 variable transposition. So the working shear stress, the stress we're allowed to use, is the ultimate shear stress, which they say is 200, divided by the factor of safety they want, and the factor of safety is 4. So 50 newtons per millimeter squared is the stress level we're allowed to use in this particular case. So what they're kind of saying is you're working down here. The maximum stress you can have is this 50 newtons per square. We're working in that region. We're not allowed to work any higher than that for the safety reasons. Okay, so that's like something from a previous work we've done where we're bringing in the factor of safety calculation. So now we've got the working stress, we can find the area of the joint. It's very much like question 2s we just looked at. We've got to rearrange the shear stress equation and find the p-value as we did before. So perhaps I'll try and do that on the left hand side here to keep it all on one slide over here. So that was the, if you like, the first step in the process in this particular case, was to find the working shear stress. So now we're going to find the shear area. Let's do that next over here. Find the shear area, the AS. Okay. So AS is equal to, looking at the diameter we're given in this particular case, it says in the question it's 25 millimeters diameter. So diameter there, the diameter, call it D, is equal to 25 millimeters. That's given in the question. So I can find the diameter, the area again. Now in the diameter it's pi D, 25 in this case, squared divided by 4. You might be using pi r squared, so it's pi times 12.5 squared for you. And don't forget, again, we add the 2 for the double shear, because we're in double shear here. Don't forget that, double shear. Okay, so evaluating the area, I get 981.7. That will be millimeters squared here. Don't forget, again, put a little note if you want to in your notes, that's for the double shear. Okay, don't forget double shear now. Alright, so hopefully that's you agree with that value there. So that's twice times the area. And the final thing now is to calculate the actual working load we can apply. So part 3 here, find the maximum shear force. Find shear force. Okay, find the maximum shear force. So from the shear stress is equal to the force divided by the area in shear. Simply rearranging again, P is equal to the shear stress times the area in shear. Now the shear stress we've worked out is 50 on the right hand side, and the area above is the 981.7. So calculating the maximum shear force, it's 49.1. I'm using kilonewtons here, kilonewtons. Okay. The maximum shear force we can take then is 49.1 kilonewtons. See how far we can get with this one here. What we've got here is a joint where we're asked to find not only the shear stress but also the tension stress in the joint, because the joint itself is in both types of failure, you could argue here. So if I was to try and sketch this, if I can sketch this too well, but what we've got basically is a plate here. plate here kind of thing, and a plate here. And we've got these two bolts going through there, or two rivets I think it is in this case, going through the joint. Right, so we've got basically a pull here, call it P, and we've got a pull here, P. And what the question wants us to do is to work out not only the shear in the rivets, but also the tension in the plate. Okay, so there's two parts to this. So I'm going to do this as two different sums here. And we've got to decide eventually what the P value, the maximum force that we can apply to the plate, and that will be based on either the shear failure of the rivets or the tension failure of the plate. We're given in the question, if you read the question, it's riveted tie bar, they call it a tie bar here. We've got to find the maximum force that the tie bar can carry. If the working stress in tension is given as 90 newtons per millimeter squared, and the working stress in shear is given as 60 newtons per millimeter squared. So we've got two calculations here. I'm going to look at the shear first because that's the one we've just been practicing. So we'll look at the shear stress first of all. So consider the shear failure of the rivets. I'm going to do that. Consider shear failure of rivets. Consider okay. So again, we're going to use the formula we've been using. So from the shear stress is equal to the force divided by the shear area. We're going to rearrange to find the shear force. P it will be is equal to the stress times the shear area. So exactly what we've been doing before kind of thing we're going to do again here. So I need to work out the area of the rivets. Now again we need to decide, is this single or double shear in our shear joint. I think we're okay to say it's single shear. It's two rivets in single shear. So perhaps I should put that down, a little note here. Alright, two rivets in single shear, so be careful of that. So our shear area then, if I work out my shear area, the AS, that's going to equal to, now let's look at the diameter rivets. It says that the diameter rivets is 10 millimeters. You can see 10 over here, 10 millimeters. So that will be pi multiplied by 10 if I use the diameter squared, and that's all divided by 4, and it's multiplied by 2 this time because there are two rivets. Alright, so it's not a double shear joint, it's the two rivets here. So I can work out what my AS is. I'll let you do the number crunching on that. According to my calculations here, the area was 157 millimeters squared. And then from that we can then find the force from the above equation. So thus the shear force P is equal to, and it's going to be the shear stress. Now the shear stress from the question is 60. Alright, so I'm getting that from the question above. Perhaps I'll write the formula down here, a bit more clarity. Shear stress multiplied by the area in shear, so that will be 60 from above multiplied by the area in shear, which is 157. So I get 9,425 newtons. Okay, and that 60 is from the above value that's given in the question. That's the allowable working stress for this shear, the rivets in shear. Okay, so what that's saying is we can apply 9,425 newtons to this joint and those rivets will then fail. But that might not be the limiting value. It might be that the plate fails before that. And we need to check the plate out. That's what we're going to do now. So that was calculating the shear failure of the rivets. That's what we've just done there. The shear failure of two rivets is what we've been looking at here. But now I'm going to look at the failure of the plate over here. So let's go consider this step now. This is consider tension failure of the plate. Alright, so this goes back to the work we did a few weeks ago. Now an engineer would say to themselves, where does the plate actually fail in tension? Where's the sort of weakest section? Now the weakest section is actually through the holes here. If I call it XX, that's the weakest section. So it's consider tension failure of plate at section XX on my diagram. If I was to saw through that plate with the holes, what I would actually see is this kind of section. There's my plate, and we're told in the question the plate is 50 millimeters in width. We know the thickness of the plate. I'm getting this from the diagram above. The thickness is 3 millimeters. Thickness is 3 millimeters, and I've got holes here and here. So if you imagine I've hacksawed through the plate, through the holes where the rivets are, that's the kind of section I would see. So imagine as my hacksaw, I would see that kind of section there, and this would be the rivets kind of thing. And we know the rivets, diameter of the rivets in this case are 10 millimeters, given in the question. Alright. So what I would have to calculate here is what's called the net area of the plate. So I've got 50 millimeter plate, and I've got two holes, if you like, of 10 millimeter width. So the actual net width of the plate is actually going to be 50 take away 20. The net width of the plate is going to be 30 millimeters. So if I put here net width, so net width of plate is going to be 50 millimeters minus 2 times 10, so 30 millimeters. Alright, so that's the net width. So that's the actual material width I've got, because obviously with the holes there, there's no material there, so you can't transfer any load through the hole there. So the width of the plate is really 30 millimeters. So if I call it L, say give it a symbol, so L, the width of the plate is going to be 30 millimeters. So the area of the plate in this case, so the area of the plate at the holes the area would be simply 30, that's the width now, multiplied by the thickness of the plate, which we can see is 3 millimeters above. So 90 millimeters squared. Okay, that's the area of the plate. We want to find the force that the plate can take here. So going back to our original formula, from the direct stress, we use a different symbol if you remember, is equal to P divided by A. Then once again we can work out the P, the force, so the tension force here just rearranging the equation, P is equal to, same kind of format, the stress times the area in tension here. Now the stress this time, from our above diagram, that will be 90. So 90 from our above table there, that's this value here, 90. I put it in yellow. That's up in the question. So 90 is shown here. Okay, that's what I'm using, and it's times by the area, which we've also said is 90. That gives a value of 8,100 newtons, what I was trying to say. Okay. So if you were designing this plate for real, in the real world, you would have to check out the shear and the rivets, which we've done, and check out the tension in the plate. It is weakest section, which is XX in this particular case. And it's the lower of the two values that limit the plate. So you can see in this particular question, the lowest force value the plate can take is 8,100 newtons. If we apply 8,100 newtons to this plate, the P value, then the rivets are okay because they can take 9,425 newtons from our calculation, so they're fine. But according to this calculation, the plate would then be over its allowable stress value, and that wouldn't be acceptable. So that's why in the question you see the answer given is 8.1 kilonewtons, or 8,100 newtons. That's because the plate limits the strengths of the joint here. Okay, that's quite a complicated question. That brings in both shear and tension into the same question, so particularly difficult there. We've concentrated mainly down on the shear stresses, but that's the kind of question you can get, those kind of questions really. What would be good in the week is if you could, if you get a chance, just look over what we've done, and any problems you've got, things you don't understand, then either email me or next week bring it to my attention straight away. Okay, but that would be really useful if you could just look over the solutions we've run through here, and then highlight to yourselves any problems you don't understand, and then we can go through things next week. Okay, thanks very much for your attention anyway. I hope it was okay from your side. I hope you're okay out there, Percy, on the tractor. Okay, still on track. Okay, thank you very much then. Okay guys, see you next week then. Cheers. Bye bye.